F324 June 12 question 4. So in this question you've got 6 marks on part A to draw the mechanism for the nitration of benzaldehyde, and you must show the role of the sulfuric acid as the catalyst. And key to it is, since that you're using benzaldehyde, this is not going to change the reaction at all. So you've got benzaldehyde here. It's not going to change the mechanism, if you like, at all, but you will need to be careful because it's told you that you're producing 3-nitrobenzaldehyde. So your aldehyde group is on position 1 of the benzene ring, and then you're going to have to count round to position 3, and that's where your nitro group will go on. So having a look at this, I need 2 acids to actually form my electrophile to start off with. They are sulfuric acid and, because it's nitrobenzene, nitric acid. And so I get my formation of the electrophile as this equation. So you've got sulfuric acid, nitric acid. Sulfuric acid loses 1 H, so it becomes HSO4 minus, plus your electrophile NO2 plus. That's the key one to remember. If you can remember that, the rest of the equation you can get, and water as well, and that gives us 1 mark out of the 6. Then to draw the mechanism, and I have drawn it out for you here, pre-drawn it, or at least someone has. You've got your 3 steps. I'm just going to talk through really these steps. So first of all, you've got your aldehyde group on there, so that's position 1. And then from there you can count round. You've got 1, 2, 3. So your nitro group wants to go on that position 3. Notice how you've got the curly arrow coming from the ring of 6 delocalized pi electrons out to the electrophile. I want to make one small correction here on my electrophile. That is, I'd rather see that plus on the nitrogen, because that is what's going to form the bond with the benzene. It's that has the positive charge. The nitrogen, you would not lose a mark for doing that, but it's better to put it on the nitrogen. So from there, remembering that your curly arrow is the movement of a pair of electrons. Oh, sorry, I didn't mean to do that. And it's coming from the electrons going to the electrophile. Then onto the intermediate. Here you've got to be very careful. I don't want to do that. Here you want to be very careful that you make sure that you have your broken delocalized ring covering 5 of the 6 carbons with the plus in the middle, orientated towards where your new part of the molecule is being added on, in this case the nitro group. Here remember, you show the H, so you've got this intermediate which has both got a bond to the NO2 and a bond to the H. What people often forget is to show this hydrogen bond breaking and that pair of electrons returning to complete the ring once more. Remember, as curly arrow, movement of a pair of electrons. So finally you get your nitro group on position 1, 2, 3, and you're left with an H plus. Notice how throughout this your aldehyde group has done absolutely nothing. It's just sat there. Marking wise, you're getting 1 mark for this first diagram with the curly arrow going to the electrophile. For the intermediate, you get 2 marks. You get 1 mark for getting the broken delocalized ring correctly orientated, and you get 1 mark for remembering to put in the curly arrow, breaking the carbon hydrogen bond. Finally, you get 1 mark for your correct products with your H+. So far we've got 5 marks. The last thing we need to do here is show how sulfuric acid acts as a catalyst. So we've got to reform sulfuric acid, and we can do that by taking the HSO4-, adding the H+ that's come from our mechanism, and giving H2SO4. So that's your 6 marks. Part B, staying with benzaldehyde, this time reacting with sodium hydroxide. Now, we've not learned particularly a reaction between benzaldehyde and sodium hydroxide, so this is all looking a bit worrying. In this reaction, benzaldehyde is both oxidized and reduced to form 2 organic products. And at this point you're thinking, oh my word, what are they asking me? Have we done this before? You just got it in the exam. Think, right, I've got aldehyde, oxidized, reduced. Do you know what happens when an aldehyde is oxidized? Do you know what happens when an aldehyde is reduced? It's going to form 2 organic products, one from oxidation, one from reduction. So if an aldehyde is oxidized, what does it form? If an aldehyde is reduced, what does it form? It's the question wants you to give the 2 organic products from those reactions. That would be 2 marks of this 3-mark question. Then it says suggest an equation for this reaction showing clearly the structures of the 2 organic products. So you're going to get marked for each of these 2 organic products, which you can draw. Then you need to think about trying to write the equation. If this was in your real exam, getting those 2 products down would be your main task. Then go on to think about the equation. So here again, it's pre-drawn out. Let's just take a look at the products first before we do anything else. So we have got an aldehyde, a carboxylic acid. My aldehyde is turned to a carboxylic acid, so oxidized. Notice here, rather than a coup, I've got cook. I'll come to talk about that in a moment. You would still have got the mark in this question if you had put an H there and just made your carboxylic acid. So you would still have got the mark if you had done that. But the cook is correct. I'll come to talk to that in a second. Secondly, here, an aldehyde reduced, and you have an alcohol. So those 2 products, 1 mark for each of those products. Now, why cook? Essentially because we have potassium hydroxide. So when you react your acid with your hydroxide, so with this alkali, it's a little bit like when you have alkali hydrolysis, in the sense that you're breaking this hydrogen bond and replacing in one of the molecules that hydrogen bond with your OK, and so you get your cook, which looks like So you've got your C double bond O, and then your O K, that's K plus, O minus. So a little bit like alkali hydrolysis in that sense that you get. That's where you get your K there. Because you've used this OK, you have 1H left over, and you've lost 1H from your aldehyde, so that this cook could have been made, which is really good, because to get your reduction back to the alcohol, you've got 1O, but you need to get 2 more H's onto that molecule, so 1 coming from the aldehyde here, 1 coming from the KOH. So that's how that reaction is working. Again, 1 mark for each of those products, 1 mark for balancing this up, so you get 2 molecules, 1 which gets its H broken off and replaced by an OK, and the second that gains the hydrogen broken from the first molecule and that second hydrogen to be reduced to an alcohol. Underneath here, very faintly, you could get the marks if you just put OH minus in. If you did that, you would just get a COO minus rather than a cook, and that was an acceptable alternative way. The balancing is the same, you still need the 2 molecules, you just got rid of the K from the KOH here and from the cook there, so that's what that little bit is doing underneath there. Part C then gives you 2 reaction schemes. Now, these 2 schemes, just having a look at them, what actually happens, because if you get a question like this, you've got to go and really look carefully and be sure you know how these schemes are working before you go into the rest of the question. So it takes part in condensation reactions, which means that we're going to be losing water, and it says that it will happen with an amine group or a methyl group. So here are 2 examples, and they've got to be adjacent to a C double bond O. So water is formed as a product, and it's got these 2 examples. So notice how, if I'm forming my water, it's this part of the molecule that is being lost, that is becoming my water over there, and this N is just simply joining this C double bond. So we've got that situation there. In fact, in the question they give us just underneath, it's H2NOH that they give us. So I can just quickly add my OH on here. That water is lost, and I'll just put my OH on there. In the question, it's still asking about benzaldehyde, so you would just pop your benzene group on here. We'll have a look at that in just a second. So that's going to be the first box in the question. Second one, doing exactly the same thing. Again, if we loop this up, it's going to take water off, so we've got that situation. Of course, there was 3 H's there, so 1 remains when we do that, and you get a water lost. So there's your water lost here, there's the H still remaining. I've joined these 2 with a double bond, so it's C double bond, and then that's the start of my second part of the molecule. You'll see H there next to the C double bond O. In the second part of the question here, they give us a carboxylic acid, so I can just put the OH on there, and then that joins, and again that is just an OH there. So the first 2 boxes are literally following the reaction schemes that they've given you exactly as they were, but just adding a little part of the molecule on in each case. I'll go down to have a look at the products in just a moment. Now, what is important is that in this question you note and read carefully the working of this word excess. Predict the organic products formed, which we have just done, following condensation reactions with benzaldehyde. In each reaction, an excess of benzaldehyde is used. Now, this is particularly important for this second reaction, because in this third box it gives us a molecule like this to react with benzaldehyde. In excess benzaldehyde, so there's going to be lots of benzaldehyde. It says that condensation reactions will occur with many compounds containing an amine group or a methyl group adjacent to a C double bond O. So they will occur with a methyl group adjacent to a C double bond O. Here I've got one methyl group, two methyl groups, both adjacent to the C double bond O. And I've got lots and lots of benzaldehyde. So the trick to this one is to realise that benzaldehyde will react this side of the molecule and lose a water. There again. But it will also react with this side of the molecule. So you can almost imagine a mirror image here of this reaction occurring on the other side as well. So again, you'll get this situation on one side and the mirror image of it on the other side. And so let's just go and have a look at these products then. So the first one, as drawn out this time with the benzene ring as well, and the second one, as we looked at above, but this time with the benzene ring on as well. So the proper answer. This third one then, what we have is, here is our ketone in the middle. Notice how each of these outer carbons have lost two hydrogens to produce the water that would have condensed both on this side and on the other side. Notice that this is our aldehyde again with our CH, the double bond to what used to be the O, which has also gone to make the water on that side, and exactly the same on the other side. I've lost from my benzaldehyde here the oxygen. I've lost the two H's from this carbon, so it's gone off to make water, and I've got basically a symmetrical molecule there, haven't I, where there's been a reaction, benzaldehyde has come and joined to both sides of my ketone. Part D, the final part of this question. Alkyllithium compounds, RLI, again something that we've not done before, can be used to increase the number of carbon atoms in an organic compound. Different alkyl groups R add to carbon chains with different chain lengths. So RLI provides a source of R- ions, which act as a nucleophile. And here we're thinking with these R- ions acting as a nucleophile, we know about reduction, hydride ions, nucleophilic, nucleophilic addition. So, and it's going to give us the mechanism. We're going to be thinking about applying our knowledge of our nucleophilic addition to this mechanism. So we've got to complete using curly arrows and relative dipoles the mechanism for stage 1, give the structure of the intermediate and organic product. Notice when it says give the structure of the intermediate, it means that we don't actually have to continue on past giving anything in the mechanism for stage 1. So it just wants the intermediate and the organic product. It doesn't tell you to do any more parts of the mechanism, so you won't be needing to add any water on. So then, as we go down, let's have a look at this mechanism. So the very first part, it gives you R minus. I suggest you put on your lone pair and then your curly arrow to the carbon of your aldehyde, delta plus on the carbon, delta minus on the oxygen, because the oxygen is more electronegative. Don't forget that you need to break this bond between the carbon and the oxygen, those electrons going to the oxygen. For your intermediate then, it is just like your nucleophilic addition. You've got your O with a minus, your R group is now bonded, you've still got that one H. You could also put a lone pair on that oxygen there. You don't need to, it's not on the mark scheme, but this is a curly arrow showing the movement of a pair of electrons. There is now that pair of electrons if you show your lone pair, though it's not necessary. Finally, for your product, you've got, like say, you've got the addition of H plus or O2 here, so you don't need to show the mechanism of that water, how it would join to the oxygen. You just need to show the organic product. Here, note just a note here, if you don't put the lone pair on, you still get the mark if your arrow goes from the negative sign. So it must go either from the lone pair or the negative sign in this case. It can go straight to the carbon atom, it doesn't need to go to the delta plus. Then here, you don't, it basically, the mark scheme says that you can ignore any curly arrows on this intermediate. If the intermediate is correct, that's absolutely fine for your mark. So you're getting 1 mark here for your dipoles and this curly arrow, 1 mark here for the curly arrow from the R to the C delta plus, 1 mark for the intermediate, and 1 mark for your product. In the final part of this question then, they give you a new molecule here that needs to be prepared using the same mechanism. It wants you to draw the structure of the alkyl lithium compound needed for the synthesis. So here, going back to our organic product above, this section here, that is equivalent to R. What you know about R from the mechanism above is that R is R, oh, here we go with the pen, is R minus. Yeah, it doesn't like me now, I'm going to stop using that pen. It's the R minus from your mechanism. So, oh, that's my cursor too. Here we go, it's back. Right, so this R group now here, it must have a minus on it. And so you've got to decide where you're going to place your lithium. Your lithium, being a positive ion, will be bonded to where there's a negative portion of the molecule. Clearly where we need to join this molecule is on this second carbon here, so that must be where the lithium was. And I think drawing it this way, though both of these structures were allowed, drawing it this way, you can clearly see that it was a lithium plus. Once that is lost, you're left with a carbon with a negative charge, so that will act as your R minus, your nucleophile. So you've got 2 options of how to answer that question there. But the best one is this one here, because it actually shows you the ions. So you need that R minus. There it is, that's where it needs to be, so that's where the lithium must be.